everyone. We're going to make today the canonical ensemble. First of all, do you have any questions? You started with stats, right? Today in the lecture? Okay. Okay, the general idea of the canonical ensemble. Do you remember for the microcanonical we had like our system, and there was like a fixed number of particles, and also what was the other condition of the microcanonical ensemble?
Additivity? No, confusing.
Yeah. There's no exchange of energy, right? The energy is constant. So we don't allow heat to go in or out from the system. That means, and since the system doesn't perform any work, that means that we have only one, only one temperature, right? But here in the canonical ensemble, what we do is that we relax this constraint. So now we allow the system to exchange energy with the surroundings. This is the change in the amount of internal energy of the system, right? Okay, so now we have this statistical quantity, which is called the partition function, right? Do you remember how we write the partition function?
Z equals I equals 1 to 0.
I'm going to put here all configurations.
Okay. Of e to the beta minus beta e.
Of the configuration, right? Okay, so this is huge, like this. The partition. Once you have the partition function, you have everything. Now we are going to discuss why. First of all, let's. What would be a physical observable that we would like to calculate, to compute? Something like the energy, right? Okay, so the energy, and since we are doing statistical mechanics, right? So it's very important that we never have an exact value for things. We have an expected value, or mean, right? We don't, like, it's not a true energy. It's some average. So how do we compute the expected value for the energy? It would be 1 over the partition function times the sum of V over R minus beta ER. This would be the expected value for the total energy. So the intuition here is that we are asking how probable is to have each configuration, right? And how so this is what we are doing with this weight, and we are asking, and this is the size of that weight on the probability distribution. Okay, so this is the usual way of taking an average. Okay, and there is a pretty neat formula to calculate actually the expected value. So do you remember that any observable that we want to take in thermodynamics is by taking some derivative of the free energy, right? Or the energy, whatever ensemble wherever thermodynamical potential we're looking. So this is true also with the partition function. So the way to compute the energy, we have this formula. Why is that? It's very it's very simple, and the idea is that we have the partition function, and if we perform a derivative over R, then the whole partition function goes down by the ln, and only the ER stays up. So this is just like a that you can actually convince yourself that this formula works. And also, sometimes we want to know the energy squared because we want to compute some fluctuations. So you know that the variance of some quantity, let's say, is given by the expected value of O squared minus expected value squared, right? So sometimes we are interested, if you want to calculate the fluctuations in the energy, we want to compute the variance. So this is also a very useful quantity. And here, the idea would be very simple. Using the first formula, we have this. Right, but this is the same. If we can take twice the derivative, right? And then we will have 1 over z. Okay. And actually, the idea is that we can, as we had with the energy, we can perform derivatives to get any thermodynamical quantity. For example, pressure, volume, anything you want in the thermodynamical picture, you can get it from the partition function in the statistical mechanics picture. Why is that? Because we know that the free energy is given by this U, right? So this is the free energy, and actually the partition function. We can compute this free energy using the partition function, which will be 1 over beta ln of z. Okay, so this is a huge connection because what we are seeing is that the partition function is the object, the mathematical object that connects the microscopic physics to the thermodynamics of the physics. Okay.
And another question is, what's the difference between the U and E?
Okay. So here when I write E, it's the average energy. So they are interchangeable, but you're going to see exactly how you can make the relation in the lectures. So I don't want to spoil.
Actually, it's the thing. Actually, it's the thing.
Right. Right.
Okay, thank you.
Right. It's actually it's the idea that we never have the actually energy. We have only an average, and that's the idea of the internal energy here. Because when we do thermodynamics, we are all like the idea is that we are only making a statistical average on microscopic physics. That's the whole idea of gating that allows us to gate with the partition function. Okay? Do you remember this story that Stas told you that solving for one particle is very easy. Solving for two particles is actually like solving for one particle, and then solving for three particles is actually impossible. So why would we be like trying to solve a problem of 10 to the 23 particles? The idea is that we don't actually care where the position of any particle is. We want to take average of things and then compute properties that we can go in the lab and check if they make sense. So that's the whole idea of the partition function. It's the bridge between the two worlds, the macroscopic and the microscopic. Okay. So actually, for example, if we would like to compute the pressure, it would be let me just put here that U is the average of the energy. Right? We know this from thermodynamics. So the only thing that we have to do, we know how to compute the partition function. So we just plug it instead of E. We just go. Okay. So we just put it in the free energy, and we get that. Just the derivative. Right. It's just the same as you would expect from thermodynamics, right? Mm-hmm. Generally, like we can always write for any given physical observable. This is the derivative. So maybe this is a bad choice of letters because this is not an X, this is a psi. And then what I'm trying to relate is that this is the conjugate variable of this, okay? Like X is conjugate to psi, and so is the volume with the pressure. Okay. So let's go and try to see how we compute partition functions. Stas told you that the only hope that we have to compute this horrible thing is doing something called factorization, right? Which is actually instead of looking to 10 to the 23 particles, we only look at 1 degree of freedom. So let's see how that works. So assuming that we have continuous variables for the energy, Okay, so this would be the canonical partition function. Okay, and sorry, let me just here. No, this goes here, and this is the volume. Right? Is it clear? Okay, so it's just the integral over the Hamiltonian instead of using the energy. So the whole idea is that this system, like we know that if we have a free Hamiltonian, that means that the particles do not interact between each other, right? So actually we would be able to write the partition function as follows. So first, for the first particle, it would be 1 over h naught. And this would be ta 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 ta, and we would have like, okay, so times all the others on the same way, right? Like this is for the first particle. The idea is that the exponent, we can write the exponent that there's a sum here minus beta, sum of over the energies, right, of each of the particles. This I is the particle, right? So this would be like E minus beta E1 times E minus beta E2 and so on, right? Okay, so if we don't have if in the Hamiltonian the particles do not interact between each other, we will see an example to see what I mean. For example, we saw last week that we have an energy that it was like free particles, only kinetic energy. So the momentum here does not depend on the ith particle, do not depend on the momentum of the I plus 1 or minus 1 particle, anything else. That's the whole idea. So then we can write the partition function. We can write the partition function for a single particle. That would be zeta. H. This is 3. Okay. So this is the partition function for the ith particle for some. Okay. Okay. Any questions about like this jump? Like how did I got from the complete partition function to the partition function of only one particle? Huh? Now that we have this zeta, which is a partition function, then we can just write the full partition function as a product from 1 to n of the partition function of each particle, right? But if we have identical particles, we have to divide actually to avoid overcounting. That's what I explained to you last week, right? So we have to divide over all the set of combinations of the n particles. And so this is very, very useful. The idea is that instead of solving a problem of 10 to the 23 particles, we actually have to solve a problem of 1 particle. And then we can do statistical mechanics. And all the idea that you will see from now on to the end of the course is how to go from a system of particles that interact between them to a system of free particles that actually don't speak between them. Okay? You will see many stories, many physical systems that behave that the idea is that every particle speaks with the other ones around them, but we can actually make a mathematical transformation to have some sort of free particles. Okay? And that's the whole idea of this process. That's the only thing that we can do to compute the partition function, because it's very, very hard in general to do. See, this is an n-dimensional, a 3 n-dimensional integral, some interaction, some arbitrary interactions. It's gross. Okay, let's see first an example. Okay, we have an n indistinguishable with 3 levels on each one, like each particle has 3 levels of energy. And we have this Hamiltonian. Okay, so we have three levels, 3 energy levels, which are 0, h, and minus h, right? And we want to compute the partition function. But here you can see that the partition function is a partition function of n degrees of freedom, right? This n. So the idea is to write but actually you can see that here the energy of the ith particle do not depend on the energy of the ith plus 1 particle, right? So we can actually just write the partition function, the partition function for a single particle, and that would be, can someone tell me how we can write this partition function?
E minus beta h plus 1 plus E beta h.
Perfect. So this would be the single particle partition function, and then it's very like what we do to compute the full partition function is use this formula. Do you know what function is this?
Cosh.
Right. Yeah,
Hyperbolic cosine.
exactly. So then we just have cosh of beta h plus 1 to the n. Sorry, this is distinguishable particles. And the thing is that if it would be indistinguishable, we would have to put the n factorial here. Okay, so this would be the partition function of this Hamiltonian. Great, and then, for example, if we would want to do the connection to the thermodynamics, we would just write minus kBt plan of cosh beta h plus 1, and here I can put an n, right? Because it goes on with the plan, and this would be the free energy. Okay? So let's go with the exercise. We're going to do a question from the exam, which I think is one of the hardest questions that Stas ever did in an exam. It's a very nice one. Till now, any questions about the conceptual picture?
Cosh is not divided by 2 if you do the
Yeah,
E.
You're right. It's multiplied by 2, right?
Yeah.
Okay. Let me write the problem and then I'll read it to you. Okay, so we have n masses with mass n, okay, which are on top of each other. Okay, so the height of the first mass is r plus y naught plus n1 h. H is a constant, y naught is also a constant. And n1 can go from 0 to infinity. Okay, and it's discrete. So let me put here that it's 1. Okay, so the distance between two masses is given by I plus 1, where I is the mass, the number of the mass. And the distance to the ground, it would be 1 plus I E naught and 1 plus I H. Okay. Here, the same I plus 1 would be from 0 to infinity. Questions?
מה רשום שם?
Here.
R I ועוד 1 שווה Y 0.
This is, sorry about my writing, n 1 I plus 1 h. It's the same of here, but with I. Okay?
With I or with 1? In the, where did you, yeah.
Here is the first mass,
The first,
right? And this is the I plus 1 mass. So it's I plus 1. Okay?
And it's multiplied by h?
Yes.
Okay.
Also here. Okay. And the distance between the I this and I plus 1 gives an energy n I epsilon 0. Okay. This is the contribution of the energy. The okay, so the interaction is a gravitational force. And the temperature is T. Okay, so we want to, this is the most important thing, write the function of the system. Okay, so the idea is that we have masses. They can go, this is the end mass, right? And they are connected by some sort of rubber band or something, in a way that it can change the height of each of the masses. This would be the ground, and this would be the first mass. Okay. And this would be this R1. Okay. Do you have any questions about the statement of the problem? If I would take the mass here, this would be the I. Let's say this is I plus 1 mass, and it would be the height would be n I plus 1 times h. Okay. And we know that the energy is a gravitational energy. So the way things interact is by m minus g h. Well, okay. Z. I'm going to put this so h doesn't seem. Okay. Any questions? The statement. Okay, so we want to write the partition function. We start with the formula, right, of the partition function. Okay, so this would be, we have n particles. Energy. Okay, and then the energy of each of the system would be we can sum over all of the masses. We want to solve from 1 to n, right? There would be this contribution from all the possible ways that. So the idea is that you can think of this as a rubber band that can only take discrete values. Do you see? Have you ever seen this kind of? Of course, in the army you have this necklace, right? Made of like.
Made of metal, like.
Yeah, exactly. Like these circles, and then you can only decrease the size of the necklace by discrete amounts, right? You can only put it here or here or here. It's the same thing. Okay, so you can increase the height of the masses only by a discrete amount. Okay. So we are done, right? Because this doesn't depend on, like, we can see that the energies do not depend between them, right? No, actually that's not true, because we see here that if we take the distance to the ground, let me call this is Ri, then it depends on all the we can see that if you want to see the height of this block, then you will have to know the distance of this mass, right, and so on. So the only one that actually, like, everyone depends on the other masses. The only one that it doesn't is the first one. So these are sideways, so it's clear that it's the distance to the ground. Is the sum over all of the arrays from I1. This is J. Okay, so in order to know for the I plus 1, we need to know how all the masses below behave, right? We always have this additive constant here, the y naught. So the whole idea is to decompose this energy that is dependent on all the other in other degrees of freedom, all the masses below the one that we are interested. But since we're interested in all the n, so everything is together, is coupled, right? So we want to decompose this. We want, actually, what does that mean? We want to find a nice mathematical trick that that allows us to treat each particle as an independent particle, a free particle, in a sense. Okay. So do you see how, like, do you have any questions of why did I write this, like, in this form? The height of the wide mass?
Between each mass there is a y0 height.
It's a y. It's a y that relates them. Between each one, there is a r plus, like, this term, the ri plus 1. Okay, and we have j terms like that, right? Like the I terms, sorry. because we are looking up to the ith particle here. Okay. Okay. So if we can perform this sum here, and it will just give you here an I, right? Because we're just summing I times a constant. So let me write it here. Either way. Here. So the energy would be epsilon 0 . Okay, I just plug in this here, right? And I exchange, since this epsilon naught does not depend on where we are standing on the chain, then you can plot that out. So now what we want to do is to decompose actually the last term of the sum, which is the only one that is dependent on the other members of the chain. Okay.
Can you explain why did you multiply the YFS in I?
Where? Here?
In the end, yeah.
Ah, yes, of course, because we are summing I times y naught, right? So we will get I times that.
Ah, okay.
Yeah, it's just a constant that doesn't depend on I. That's the idea.
Okay.
Okay, great. So we have this thing that we have to take care on, I, J, and J thing, that it's the only thing that this is this term, right? So so in order to see what is going on,
Wait,
let's start.
The sum there is from j equals 1 to j.
Ah, I.
Okay.
Sorry. And this is J. Thanks. Okay, so let's start computing for I equal 1. Right, so if I equal 1, then this just equal 1, and what we have? Just n1, right? Okay, do you see why?
And then it's
This
like,
is, okay, let me put here. This is an I, okay? So, I is 1, okay? This is goes from 1 to n, okay? Let's start with I equal 1, okay? So here it's from j1 to 1, so then this is n I, right?
and then we have plus n1 plus n2,
Exactly.
and then we have n1, n2, and 3. And
Exactly.
so on and so on up until n.
And then until n, right? You're absolutely right. Do you see why? Yes? Okay. So then we can just say, how many times will n1 appear?
And big N.
Right.
And then we have big N minus 1 and 2, and so on and so on.
Perfect. Okay. So in another way of saying that is just sum over n . Okay, so we have this. Let me this in brackets. Okay. So once we have achieved this, we are done. Because actually now you can see that this each term on the sum does not depend on the other terms, right? Because ni does not depend on the terms of the other places of the chain. And this is I, which of course doesn't depend on any other terms on the chain. Do you agree with me?
Wait, why do we have like 2 times capital N? Like n times n, isn't it should be like only 1?
Right. Ah, sorry, and minus.
Yeah, like this.
Right?
Yeah.
Okay. So do you know what this gives you from 1 to n? This is I. These have a pretty neat result. This is n. Gauss said that he computed this formula when he was 5 years old. Just as a story. When he was being punished in school, like in first grade. Okay, so now the energy, we can write the energy like this, epsilon naught. Right? Because I only put this this nice formula here in this I, and then I substituted here, and then we don't have anymore the sum over j. It's only a sum over I, right? Here, everywhere. Okay. So now we can write the partition function for a single particle, right? Right. Do you agree? Okay, great. Let me just close these brackets. Now n, like we would have to sum over all possible n's, right? And so here I missed the. This is the Boltzmann weight only. This would be a sum over n I equals 0 to infinity, right? Do you know what is this called? Like I can put this ni here, right? Because it's an exponent.
What code?
This thing. Okay, so then the ni was here, right? but I can put it actually here to multiply everything, right?
Why?
Here, because I'm only doing this, right? Okay, and then this is just a geometric series on NI, right? This is very important that you, okay, so that you actually see that this result, you will see it many times during the lectures, but this actually gives you something like this. Right? So this is just putting the geometric series is like this. Right? This is what just plugged here. And then the full partition function is just a product of those things. It is very important that you understand the general philosophy of the trick. That we have a bunch of degrees of freedom that interact between them, and then we need to find a neat or some mathematical trick that allows us to decompose the interaction, like if they were like free particles in some sense. And okay, this will be the full partition function. Do you have any questions? Anything? Okay, so the idea is that I only multiply this many times, and this term is independent from the I, right? And then I only have the I independent term. Okay. Do you have any questions? Was it clear? I don't know. This is a bit of a messy example. Okay. So see you next week.
Thank you.
Should build it.